So now limit laws for sequences. The limit laws given in my earlier videos also hold up for sequences, and their proofs are similar, i.e. we essentially just replace the functions with sequences as per theorem 1, because all we are changing is instead of dealing with all numbers, we're dealing with integers only. So we can just write these down, and yeah, they're exactly the same. So if the sequences an and bn are convergent sequences, that is, they have limits and c is a constant, then we have the following limit laws. So we have limit as n approaches infinity of the summation, so an plus bn. This just equals to limit as n approaches infinity of an, and then plus the limit as n approaches infinity of bn. So we can separate those out, and even if it's subtraction, we could add the same thing. Let's put a negative here. So plus or minus an bn is going to be the same thing. We just separate the limits plus or minus like that. Just to save time, just put a plus or minus. So now if we have a constant now, so limit as n approaches infinity of c times an, this just equals to, we'll take the constant out, so c times limit as n approaches infinity of an. And also, side note here, limit as n approaches infinity of c, the constant just says equals to c. So yes, so this is the same thing as the multiplication one, but the limit is c. So let's do the multiplication now. Limit as n approaches infinity of an bn, this equals to limit as n approaches infinity of an, now times this by limit as n approaches infinity of bn. So we just multiply the limits together. And likewise for division, so if we have limit as n approaches infinity of an, like this, an over bn, this equals to the limit as n approaches infinity of an over limit as n approaches infinity of bn. And this is if bn is not equal to 0, otherwise we'll have undefined, well, divided by 0 goes to infinity, or can go to infinity. So we can't have that. And now the last one is the power rule 1, so limit as n, this one I went over for the just general function in earlier example. So limit as n approaches infinity of an p, this equals to, well, we could take this all out. So we take this whole p out, so we'll have limit as n approaches infinity of an of p like this. And this is if p is greater than 0, because if it's less, we're going to have some inverted scenario, and where an is greater than 0. Yeah, so if it's less, we'll have a fraction and so on. So we will not be dealing with that, and well, if we do, we need to manipulate the function a bit more. So this one is for p is greater than 0 and a